My name is Cheng Fang. Come from audit. My English is not so good, so if you couldn't understand what I'm talking to you, welcome and feel free to come to me after my speech and complain. Yeah. Today I'll talk about a topic which might sound a little normal or not very important. The topic is dependency management. But that's just the simple side of it. Today, I will go deep with you. We will explore its complexity, its risks, and the answer we finally found. First, I want to start with a story, a real story that I was part of. I was on this project from the very beginning to the very end. A few years ago, a government questioned if a large telecom company's product had a backdoor. Maybe some of you have heard of this. What is the most direct way to prove that a product is safe and has no backdoors? It's to review the source code, right? It's so obvious. So this company gave all of its product source code to the government, and the government worked with several top security and software companies. It took them almost half a year auditing the code line by line. After 6 months, the government admitted that the source code is clean and they found no backdoors. So the first question, the source code is clean. Does that mean the product is safe for sure? Yeah. So, but some people will say, yeah, it seems the product is safe, but actually it's not. So the government asked a second and much deeper question. We agree your source code is clean, but are the products we bought from you and deployed in our private network really built from this source code? This is a very reasonable question. What if the company uses one set of source code with backdoors and gives another set of source code, clean set of source code for the audit, right? And also reproducing a project from source code sounds simple, but if you have experience, you know how hard it is to reproduce a project from source code in a completely new environment. And also, this is also a huge system. It use many programming languages like C++, Java, Rust, Go, TypeScript, Python, Perl, a lot. And it had a very complicated build process. And there was more. The government's requirements was extremely strict. First, the build must be reproduced in an infrastructure that the government completely controlled. The government don't want to use any of the company's internal built environmental pipelines. Second, the product finally built must be bit for bit identical to the product deployed on the equipment. Even if there are differences, these differences must be explainable. For example, the difference caused by file paths, the timestamps, random sorting. So this was an almost crazy task, right? To complete, the company spent another half a year. Thanks to the hard work of the company's engineers, the build was successfully reproduced in the government's internal environment. So the government had to admit, yes, the products they bought were indeed built from this audited source code. So the source code is safe and the product are actually reviewed from the audited source code, it should be trustworthy, right? It seems there are no more problems, right? But the government asked the third and most critical question. How can you prove that in such complex build process, every single step is safe and is secure and is auditable? How do you prove there was no chance to secretly introduce any security risks or backdoors? These questions sound like they are trying to find some problems, but there are not, right? But if you think about it carefully, this question is no longer about the source code or the product. It points at directly at the core of modern software engineering, the production process. Because it touched every part of the software production that we can't see or touch, but that really exists. For example, which version of compiler you use, and are there any hidden tasks in the build script? Could the tools used during the build process intentionally modify the source code or change the result? This is not just worrying about nothing. Last year, year 2024, the XZ incident was a typical example. The attacker didn't modify the source code. Instead, they injected the source code, injected the backdoor by changing the build script. A source code audit was never funded. So if it wasn't found by an accident, a huge number of network servers on the world in the world would widely open. This was the hardest task. To prove it, the company spent almost another year to prove that every single step in their build process was secure. Maybe some of you might remember the news from a few years ago about how the story ended. Even though the company proved everything, but the government still decided not to buy from them in the future, and they plan to completely replace the company's product. And within a few years. And it looks like the company wasted almost 2 years and a huge amount of work and money. However, the company's leadership didn't think so. They thought it was a great opportunity to learn and to improve their engineering capabilities. So they continue to invest a lot of money. In the 5 years since they started dealing with the government's questions, they invested about $2 billion US. This money used especially used for research and practice to improve their engineering capabilities. And they even wanted to invite the guy from the government who asked these 3 questions. They want to thank him properly because his 3 questions help the company see the deepest challenges in their engineering system. So this led them to a core conclusion. In large scale, complex systems with long life cycles, trust is no longer just a feeling or a promise. Trust must be designed and implemented. Trust is an engineering capability. The story I just told was not just about a company's crisis management. Through the 3 deepening questions, it perfectly shows us the 3 core challenges we all face in large-scale software engineering. The first question is source code trustworthy? Behind this question is really asking, can we clearly define and manage all the inputs that make up the software? This connects to the first practice we will discuss today, chunking. The second question, is the product really built from the source code? This question challenges us. Can we make sure the whole product process from input to the output is reliable, deterministic, and free from interference? This connects to the second practice, fabrication. The third question, is the whole production process trustworthy? This gets to the core. Can we provide undeniable proof for the final product to show that its origin is clean? This connects to the third practice, verification. Next, we will focus on the three practices and discuss what real-world challenges we will meet. Okay, so to implement the three practices, chunking, fabrication, and verification, what is the common object they work on? What exactly do we need to manage to support this system? The answer is our real topic for today, dependency management. When we talk about dependency management, most of developers think of the dependencies in the file package.json, the dependency tag in the pom.ml, the require in the file go.mod. We know that changes to these dependencies can cause can affect product features and the build. And if they are wrong or missing, it will cause functional problems or the build failures. But is this everything about dependency management? Are these the only changes that can affect the product features and the build process? To truly understand the dependency management, we must look from a higher perspective. We need to look at the entire build process. You will find, besides the code dependencies we usually know, there are more. For example, which versions of compiler you are using. This is a two-chain dependency. Small differences in an environment variable, it's an environment dependency. And compile options in a make file, it's a configuration dependency. Or template files used for code generation, it's a data dependency. And the changes to these things can cause product failures or introduce critical issues, like code changes can. And their changes have the same impact on the product features and the build, like those software packages. As we develop, those things also change and get upgraded. So why can't we also call them dependencies? So everything that affects the software production process and its final result are dependencies. We can call them general dependency. And the traditional dependency we usually think about, we can call them narrow dependency. When we understand the general dependency, we must treat them like we treat narrow dependency. We must treat them like code. And more importantly, we must establish their relationships and manage these relationships. How complex is the general dependency network in the real world? Let's look at a real case from a huge telecom product. Look at these numbers, 1,000 code repositories, 9,000 components, 84 million lines of code. This is really a huge project. And it has been developed by 1,000 developers for for almost 15 years. And it has to support complicated customization requirements for many different customers around the world. Why? And also the picture on the right looks also very complicated. But this is only 15% of the entire system's build view. Why do we look at a case of such large scale? Because as the scale grows, many small, minor problems we usually ignore will grow rapidly. A larger scale of their development environment is like a magnifying glass. It helps us see the real reason behind many problems. When the general network becomes so huge and most of it is invisible, the pain points in our daily work appear. Maybe everyone here, no matter your roles, has had a similar firefighting experience. We've all had a headache about building efficiency and reliability. Maybe you don't change any code, but the cache suddenly becomes invalid, or a part that needs to be rebuilt, but incorrectly use the cache. We've all been frustrated by the reliability of CI/CD. It works on your local machine, but it fails in CI, or it fails in CI, but you can't reproduce the same errors on your local machine. We've all been anxious about the security risk tracing and architecture governance. A security scan reports a high risk, but nobody can explain where it came from. Or two components that were designed to be independent, but now they secretly depend on each other. These chaotic situations can be summarized into three core challenges. Three core challenges. The first is unclear path of change impact. A small change to a low-level library, who will it affect? How big is the impact? Nobody can say for sure. And accurately estimating an impact scope becomes an impossible task. And usually the impact change, the impact change in the build and the development environment is often ignored. An apparently normal two-chain upgrade can break the whole pipeline and cause constant errors. The second challenge is integration is late and fragile. As the scale grows, we have to make a painful choice between fast but incomplete and complete but very slow. And our full integration process is full of manual work and prayers. The third pain point is slow builds. If a full integration build takes 7 to 8 hours, which means after a developer pushes his code, his commit, he has to wait until the next day to see the result. To speed things up, we make a compromise. We only do partial integration and testing for the code change. But this just postpones a larger integration problems to a later full integration stage. For example, like a weekly or monthly full integration build, and the teams have to spend days and a week or even more to fix these accumulated integration problems. Facing such difficult situation, we must evolve. At a small scale, we rely on we rely on a black box scanning model of build tools. For example, when we run make, it scans all the files on its own and figures out what to do. This is very direct and effective. But as skill grows, even if you don't change anything, just this scanning of everything is becoming a massive waste of time and resources. This is the biggest bottleneck in the larger scale software development. I once worked on a project with 2 million lines of code, with 2,000 developers and millions of lines of code, and it used Bezel for building. Bezel is a famous build tool from Google. At this scale, the bottleneck of black box scanning was very clear. There are two huge time costs here. First, if you change nothing, just starting the build and having the tool loaded all the packages for an integration build, this full scan phase takes 6 to 8 minutes in our setup. Second, in a full integration build, the cache for that build would total about 40 gigabytes if we download all of them. In each run, we still try to download as little as possible of the cache, often 100 megabytes to several gigabytes, made up of a lot of small files, which takes about 10 minutes. You can imagine it. On the CI pipeline, thousands of build nodes working at the same time, and they all doing this full integration package loading, and at the same time, they all trying to download these small files, which easily cause a network storm and slows down the network and cause everyone's build time even longer and unstable. So a new model is a necessary choice. That's it. Explicit engineered governance. Simply put, it's divide and conquer. The core idea behind this is very simple. We can no longer passively rely on tools to discover things. We must proactively and explicitly define and manage our engineering system. This is also the foundation for many stable, effective, distributed build system. By breaking down a larger project into many independent build units, we can send those build tasks to many different machines to run in parallel, right? This divide and conquer is fundamentally different from the partial integration we did in the past to speed things up. In the past, we did partial integration based on developers' experience or just gut feeling. It's easy lead to wrong estimations of the impact scope, and it's easy to miss hidden dependencies, and it pushes all the problems and issues to the later for integration stage. The divide and conquer I'm talking about here is based on a precise and explicit general dependency network, and it's a systematic and predictable way breaking things down. It's not just build less, but to precisely build only what is necessary. For developers, the experience changes from to be fast, I only build and test a small part and praise and nothing breaks, to I run global integration and build and test every time, but the system can finish it in a few minutes. So how do we achieve this? There are 3 core practices. The first is chunking. We break down the system. The goal is to create small, independent build units with very clear boundaries. And we are not just splitting the source code, we are splitting the entire build context. And the second practice is fabrication. We build the product. Once we have clean, well-defined build units, we need a reliable build process to assemble them into a final product that can be delivered. The third practice is verification. We verify the result. We need to generate a birth certificate for every artifact we build to prove that it was made from the exact inputs we declared and nothing else. All right, let's look at these three practices in more detail. We will see what real-world challenges each one fixes. Let's start with chunking. The goal of chunking is very simple. It's divide and conquer. But for this to work, every build unit must have very clear boundaries, and its list of dependencies must also be 100% complete and accurate. But why is this so difficult? The first challenge for chunking is that our build units don't have clear boundaries. To simplify maintenance, we usually manage our environment dependencies centrally. This can be convenient, but it makes the dependency boundary unclear. The dependency boundary for our build units unclear. This makes the chunking difficult. You have to guess about the dependencies. If you declare too many, you waste time and resources rebuilding things that have not changed. If you declare too few, you will get strange caching errors or integration problems. And the only solution is to clear the cache and try again. So what is the fix? We must chunk the entire build context with precision. We need to think beyond just the source code. We must consider everything: the toolchains, OS libraries, environment variables, configurations. Every build unit gets its own clear, independent build context. And when these build units are merged, we have to explicitly fix the conflicts between their general dependencies. The second problem is the hidden dependencies. These are things we often take for granted. For example, an environment variable on the CI server or a specific OS library versions in a Docker-based image. These things can break your build, but they are often not documented or tracked as dependencies. The fix is to identify and manage every hidden dependencies. We must make the invisible things visible. Everything that affects the build and the final result must be versioned and declared. If you already use infrastructure as code, that's a good start, but we must go one step further. We must connect that infra code to your application code. Once you do that, the build system can automatically provide correct versions of everything, from a compiler to the entire build environment. The third challenge for chunking is broken connections. For example, how does a Java service depend on a C++ library, or a C++ library depend on a Rust library? And the build often this kind of connection is hidden in the complex build script in our pipeline. And the build tools for each programming language don't know this connection exists, right? And an even worse problem is ghost dependencies, like using relative paths. This kind of dependency, this kind of connection is completely invisible to the build system. The solution is to use declarative relationships for all connections. We must stop using temporary script or relative paths to connect build units. Every connection between the build units must be explicitly declared and managed by our build system. The chunking gives us the clean, well-defined build units. And now let's move to the second practice, fabrication. The goal of fabrication is simple to say, but very difficult to achieve in practice. For the same set of inputs, always produce bit for bit identical output. This is the core idea of reproducible builds. Why is this so tough? First, our build process is often unreliable. It might try to access the network or depend on the current time, and it gets worse with manual hotfixes. We've all been there. We apply a quick patch in an emergency, and these changes are usually untraceable and bypass the standard process. So how do we fix this? The key is to avoid letting developers write the build logic directly. Instead, we treat the whole build system as a proper software production. We build a simple declarative DSL so developers can easily declare what they need, not how to build it. The old way was to use rulebooks or checklists with ask developers to follow these guidelines to make their builds hermetic, deterministic, and idempotent. But this approach is fragile. It's easy to get wrong. It depends on developers' experience, right? So we made a fundamental shift. So we made a amount shift that it's no longer the developer's job to remember the rules. It's the build system's job to enforce them by design. And the system itself guarantees every build is sealed off, is predictable and repeatable. And we moved from relying on human discipline to getting these guarantees automatically. And this isn't just fix the reliability. It makes the entire build process much easier to use and maintain. The second practice is what I like to call config hell. As we support more platforms and more customers, we get a product configuration explosion. The logic for each customization is often buried in a massive and complex web of if-else statements. A tiny change in the logic can easily cause unexpected bugs. To get out of this mess, we need a more declarative approach. In highly customized multi-platform scenarios, the configuration should be treated primarily as data rather than not code. Every product has its own unique configuration. Any change to a feature is simply a change to this config data. We use a unified business-focused language for these configs, like feature flags or compile options. And this lets us declare what a product does from a business point of view. And this approach simplifies the build logic and decouples the business features from platform-specific details. And make our product much easier to manage. The last practice is verification. Chunking gives us, after chunking, we know our inputs. After fabrication, we have a reliable process. Verification is bought to prove it all. The goal is to create a birth certificate for every artifact we build. This makes the entire process transparent and more traceable. And I mean every artifact, every library, every PR build, every single thing comes out of the system gets its own proof of identity. So why is building this chain of the evidence so hard? Because traditionally it's broken. The story with the three questions shows us exactly why. The third question is the real wake-up call. It forces us to see the every node in our general dependency network graph. To build an unbreakable chain of evidence, it must be both complete and accurate. Completeness means the evidence chain has to cover the entire general dependency graph. And we have to prove where every dependency comes from, or their trusted sources. And especially the third-party ones, the third-party ones. It's not enough to just list them. We must record how they were built or their trusted source. And we also must record how the dependencies are connected, capturing the connection logic from the build rules, and not just that a connection exists. The accuracy means the evidence chain must perfectly mirror its final artifact. Any change to an artifact must correspond to a change to its evidence chain. And this works both ways. A change in an evidence chain explains why an artifact is different. This makes everything traceable and auditable. Have you realized that some of the problems we discussed today, like building efficiency, reliability, security risk tracing, CI orchestration, architecture governance, these things seem separate and isolated in our daily work, but actually they all share a common root. That is the lack of general dependency management. And through the chunking, fabrication, verification framework of explicit.
So, everyone looks very hungry and thirsty.
Oh.
Thank you all for having a great day.
Through the
going back to dinner at the same place as this morning. Bastian is there. You get a few coins to get some drink. Just kidding.
Through the framework of explicit engineered governance, we can fix these problems in a single unified perspective. What are the real-world benefits from this practice? Let me share some powerful examples from our practice. These are real, these are true. First, the CI pipeline orchestration. Our full pipeline, which supports every single code commit, it had almost more than 300 tasks in the build pipelines with very complicated dependencies between them. You can imagine how difficult and expensive to manage a pipeline of such scale, large scale. With precise and explicit general dependency management, we can automatically orchestrate and optimize it. And we found, in our this case, we found in most of the time there are only about 20 tasks are actually affected. The system can automatically identify the exact impact scope of any change, and then it generates a unique one-time pipeline only for that change. And the pipeline only contains the tasks that need to be rebuilt, tested, and integrated. From more than 300 tasks to about 20 tasks, this massive reduction not only boosts the CI efficiency, but it also takes a huge load off our build servers and the schedulers. In this case, this less than $30 million in savings on build infrastructure cost in just 1 year. The second case from the autonomous driving department, they have to support multiple car manufacturers with each with different car models, and every car model has different hardware, sensors, features. In the past, they need about 2 months, more than 2 months, to add support for a single new car model because they have to modify the very complicated build script in their build system. After moving to a system that where every car model has its unique explicit configuration, they can now add a new car model in just 3 days. And in fact, every car running on the road using their autonomous driving software is built with this system. And they have used this system for more than 3 years. I was so proud of it. And also, our system can generate the pipelines that are independent of the CI server. For example, the system can generate a local pipeline, build a pipeline, using a makefile. Yes, you heard that right. A makefile for a complex systems build pipeline. Actually, the build logic, the pipeline, usually we run the pipelines on the Jenkins server or the GitHub Actions, right? But the tools that run pipelines doesn't matter. The build logic should be identical. And this is critical because our system's build logic should never be tightly coupled to a specific pipeline environment. And also the secret risk tracing, we can identify and track the security risk in just a second, and also the architecture governance. If a developer introduce a connection between two components that were supposed to be independent, the system can flag it immediately after the code is committed. It might signals a potential violation of our actionable design. and trigger a focused review by our architects. So where do we start? Here are two concrete things that we can start working on. The first is refactor your build scripts. No matter what you are using, Bazel, CMake, Make, Gradle, and whatever, and start moving away from complex if-else statements or step-by-step imperative commands, and towards to a declarative style. This is not just a cleanup. This makes our build system much easier to use and maintain, and much easier for developers to understand. And it turns our build configuration from a program that everyone is afraid to touch into a clear map of our system's architecture. The second is automate your entire infrastructure setup. You can ask your team this question. If our CI/CD was completely wiped out, how long would it take to rebuild it from scratch? I've asked this question many times. If the answer is, we probably couldn't, you have a serious problem. You should be able to automate your entire the CI infrastructure with just one single command. This is not just for disaster recovery. It forces you to treat your infrastructure as real code, which brings consistency and predictability. And it turns your CI infrastructure from fragile manual setup into a reliable version-controlled asset. Okay, that's all for my sharing.